Today we are going to learn about mastering adaptive gradient descent techniques. We will explore adaptive algorithms like AdaGrad, RMSProp, and ADAM, crucial for optimizing neural network training. By the end of this video, you'll know how to select and implement the right adaptive gradient technique for your machine learning tasks.
Welcome to our deep dive into the world of adaptive gradient descent techniques. As the name suggests, adaptive gradient descent refers to a category of optimization algorithms that adjust the learning rate dynamically during training. These techniques are vital for training neural networks, especially when handling large datasets, which are common in today's data-rich environment. Today, we'll focus on three popular algorithms: AdaGrad, RMSProp, and ADAM. Each of these methods offers unique advantages and is suitable for different scenarios. By the end of this video, you will not only understand how these techniques work but also gain the skills to choose and implement the most appropriate one for your specific machine learning tasks. Let's embark on this journey to mastering adaptive gradient descent techniques. AdaGrad, short for adaptive gradient, was one of the first adaptive learning rate algorithms. It adapts the learning rate for each parameter during training, making it particularly effective for dealing with sparse data. The core idea behind AdaGrad is to maintain a per-parameter learning rate that decreases over time, which helps the algorithm to focus on infrequent features. This is particularly useful in natural language processing, NLP, tasks where some words appear less frequently than others. The mathematical foundation of AdaGrad involves accumulating the squared gradients for each parameter, which adjusts the learning rate based on their historical gradients. Despite its advantages, one downside is that AdaGrad's learning rate can become excessively small, leading to premature convergence. Nevertheless, understanding AdaGrad is crucial as it laid the groundwork for more advanced algorithms like RMSProp and ADAM.
RMSProp, or root mean square propagation, was designed to resolve some of the limitations of AdaGrad. It modifies AdaGrad's approach by introducing a decay factor, which prevents the learning rate from becoming too small. This makes RMSProp particularly well suited for non-convex optimization problems inherent in deep learning. The algorithm maintains a moving average of the squared gradients, allowing it to adapt the learning rate dynamically without the excessive decay seen in AdaGrad. By using an exponential decay average, RMSProp ensures that the influence of past gradients diminishes over time, stabilizing the convergence process. This quality makes RMSProp a popular choice among practitioners, especially for training recurrent neural networks where gradient vanishing issues are prevalent. Understanding RMSProp's benefits is essential for anyone looking to optimize their neural network training effectively.
The ADAM optimizer, short for adaptive moment estimation, is an advanced optimization algorithm that combines the strengths of both AdaGrad and RMSProp. It utilizes moment estimates to adapt the learning rate for each parameter. ADAM maintains two moment estimates. The first moment estimate is the mean of the gradients, while the second is the uncentered variance of the gradients. Additionally, ADAM incorporates a bias correction mechanism to deal with the initial moment estimate's bias towards zero. This allows ADAM to perform well in a wide range of tasks, from computer vision to NLP. The adaptability and robustness of ADAM have made it a default choice for many deep learning applications. By mastering ADAM, you will enhance your ability to train models efficiently, even in complex and diverse scenarios. To effectively choose between AdaGrad, RMSProp, and ADAM, it's important to compare their performance across different tasks. The criteria for comparison include speed, accuracy, and stability during training. AdaGrad may perform well on sparse data but can struggle with larger datasets due to its declining learning rate. RMSProp offers a balance with its decay factor, making it suitable for non-convex optimization tasks. ADAM, on the other hand, provides versatility and robustness across various scenarios, making it a preferred choice for many practitioners. The performance of these optimizers can also vary based on the size of the dataset and the specific task at hand. Understanding these performance nuances will guide you in selecting the most appropriate optimizer for your model, ensuring optimal training results.
Selecting the right optimizer is crucial for the success of your machine learning model. Several factors can influence your choice, including the specific requirements of the task, characteristics of the dataset, and the complexity of the model. For instance, if you're dealing with sparse data, AdaGrad might be appropriate due to its adaptive learning rate for infrequent features. For non-convex tasks, RMSProp might offer a better balance. ADAM's versatility makes it a strong candidate for a wide range of tasks. To make an informed decision, consider the trade-offs between speed, accuracy, and stability. By understanding these factors, you'll be better equipped to choose an optimizer that aligns with your model's needs, ensuring efficient and effective training. Let's move from theory to practice by implementing these optimizers in Python. We'll start with AdaGrad, where you'll learn how to code its adaptive learning rate mechanism. Next, we'll implement RMSProp, focusing on its decay factor and moving average calculations. Finally, we'll code the ADAM optimizer, highlighting its moment estimates and bias correction feature. Throughout these implementations, we'll provide code snippets and detailed explanations to help you understand the underlying processes. Additionally, we'll discuss common pitfalls you might encounter during implementation and offer solutions to overcome them. By the end of this section, you'll have hands-on experience in coding these adaptive gradient descent techniques, equipping you with practical skills for real-world applications. Even with the right optimizer, you may encounter challenges during training. Common issues include slow convergence, overfitting, or underfitting. To troubleshoot these problems, start by examining the learning rate and other hyperparameters. Adjusting these can significantly impact the model's performance. Monitoring convergence through visualization tools can also help identify issues early on. If problems persist, consider revisiting your dataset or model architecture. Experimenting with different regularization techniques or data augmentation strategies might also yield better results. By applying these troubleshooting tips, you'll enhance your ability to optimize models effectively, ensuring that you achieve the best possible outcomes in your machine learning projects. In conclusion, we've journeyed through the intricacies of adaptive gradient descent techniques, exploring AdaGrad, RMSProp, and ADAM. These algorithms play a crucial role in optimizing neural network training, particularly with large datasets. We've examined their unique advantages, practical implementations, and strategies for selecting the right optimizer for your model. With the skills acquired today, you're well equipped to tackle various machine learning challenges using adaptive optimizers. As you continue your learning journey, consider experimenting with these techniques in your projects. We encourage you to apply what you've learned, refine your skills, and push the boundaries of what's possible with adaptive gradient descent techniques. Thank you for joining us, and we look forward to seeing what you'll achieve with these powerful tools.